Welcome back. In this lesson, we're going to look at the classification of stars. So when you look at a star through a telescope or when you chart where something is, what's going on with that star? We're going to start by looking how bright a star is. And one of the ancient Greeks, who was a well-known astronomer, was the first to look at stars and say, oh, some are brighter and some are dimmer. And he classified those stars between a 1 and a 6. So 6 was the very faintest stars that he could absolutely make out on the clearest night. A 1 was the very brightest stars. Okay, so if you were to have a classification of 1, and this is Hipparchus was the name of this guy. Hipparchus's 1 would be a really, really bright star. A 6 would be the dimmest possible star that you probably couldn't see. If you had any light pollution at all, you wouldn't be able to see a 6. Now, we, of course, are using telescopes. We can see way farther than you can with your eye. So there are many, many stars beyond a 6, and there's a lot of brighter stars than a 1. So you can even have negative values for this. But we've kept this old system of 1 to 6. A 6 is about 100 times dimmer than a 1. That's how it is. And so you've got this mathematical scale that we can keep up. And so you have stars, obviously, that are going to be, bright, and then stars that are going to be dim. But there's a problem here. If I were to put a flashlight in your face, real close to your face, it would appear very, very bright, even though a flashlight is not going to be as bright as, say, a burning ball of gas in the sky. So depending upon how close a light is to you, it appears brighter just because it's close. So some stars appear very, very bright. Does that mean that they're enormous and that they're putting out tons of light? Or does it just mean that they're closer? So some of the stars in the background could be much brighter stars, that they're putting out more energy than what looks brighter. So the first thing I need you to know is that there is a way that we can classify stars just by apparent magnitude. Okay, so apparent magnitude is how bright does it appear. Okay, how bright does it look like it is? Now, if I knew that you had a bright light shining on you from 100 feet away, and a not so bright light shining on you very, very close, and the dimmer light appears to you to be brighter, as long as I could tell you, oh, well, this one is farther away, exactly this far away, then you could rate between the two lights exactly which one is actually putting out more energy. Okay, so if I knew the distance to a star and I knew its apparent brightness or apparent magnitude, then I could figure out its true brightness. How much energy is it actually dumping per second? And if I could know that, then I could judge all apples to apples, and I could look at every star and say, this is an enormous star, here's the temperature of that star, this one's a colder star, this is the temperature of that star. And so by figuring out distances, I could fix a whole lot of things. So distance is a little bit of a trouble, okay? There are two ways to figure distances. If you have something short, around 300 light years away, okay, something closer or about 300 light years away, you can look at how the star changes based upon where you're looking at it from. Okay, so imagine that you're looking at your thumb. Okay, now close your right eye and you're looking at your thumb through your left eye. Now you close your left eye, you're looking at your thumb from your right eye. That thumb will appear to change places. Okay, it looks one way and then it looks another way. As you're looking at it, it's going to appear to move. That's called parallax or stellar parallax. Okay, so you can say, okay, well, based upon where it appeared to move, how far away is my eye from my thumb? Okay, if it moves this far, it must be this far from my eye. If it only moves this far, it must be farther away. So move your thumb close to you, look at through one and another, and you'll see that the distance is far. move your thumb very far away from your eyes. Now look at one and then the other, and you'll see that it doesn't appear to change as much. So based upon us looking at a star, say in January when we're on one side of the sun, and I look up at a star, and then I wait 6 months, okay, till the summer, look at the same star, and then say, how far did it appear to change? I can figure out a distance, okay? Farther than 300 light years, there's some other tricks that you can do through some variable stars, and we'll look at that later. But if I can figure the distance, then I can figure its true brightness. And then if I can figure out its true brightness, I can classify all stars together, and that's what we're going to look at in this lesson. We're going to look at a diagram called an HR diagram, or a Hertzsprung-Russell diagram, and it basically charts all the stars that we know, and then you can add stars as you learn about them, right? So the Hertzsprung-Russell diagram, or the HR diagram, is based upon two things. It's based upon how bright a star is and its temperature, because we can figure out some other things with temperature. In the previous picture, some of those stars looked blue, and other stars looked white, other stars looked red. Okay, so based upon the color, we can basically say the cooler stars are going to be towards the red end of Roy G. Biv, and the hotter stars are going to be towards the purple end of Roy G. Biv. And so if we know its temperature and its distance, we're going to plot a diagram and put every star that we know on this diagram, and that's what we're going to look at to do the Hertzsprung or Russell or HR diagram. Okay, not to hold you in suspense, I'll show you an HR diagram in just a minute, but you're going to see in the middle of the diagram there's lots of stars all in a straight line, kind of an S-curve line, and these are called main sequence stars, and most of the stars are going to be main sequence. Okay, so our sun is about a 4.3 main sequence star. In the upper right, you're going to see the giants. These are huge, very, very bright stars, and they're even bigger stars than giants, called supergiants. And then in the lower left, you're going to see what are called the white dwarfs. They're not very bright, but they're very, very hot. And so we'll look at these in a second. Okay, finally, I'm showing you a picture of an HR diagram. You can see that there's a line or a strip, kind of a curvy SE line in the middle, which are about 95%. So about 95% of all the stars are in this sequence here called main sequence stars. Our sun is right about the middle. This is we have a yellow star. And you're also going to see that I've got 4 different sets of information along the bottom and the sides. Okay, so first of all, along the bottom, we have cooler stars here on this side, on the right side. We have hotter stars on the left. So anything going towards the left is going to get hotter, hotter, hotter. You're also going to see that those stars change color kind of based upon the rainbow. So the cooler stars are going to be red, and then orange. You can see some orange stars, and then the yellow, like our sun is yellow. And then as it progresses, you can have into the blue and deep blue stars. Now, the cooler stars are going to be on the right, so these are cool stars, and then the hot stars are going to be on the top. So anything towards the right is cool. Anything towards the left will be hotter as it goes towards the left. As it goes up, you're getting luminosity. So let's look at the right first. The absolute magnitude, okay, so you can have, this is based upon, remember, 2 different things, distance and apparent magnitude. So apparent magnitude, what it appears to be, plus how far away it is, and then you can judge them, like I said, apples to apples, all of them equal in terms of how much power are they sending out. And then on the left, you have luminosity. And all that is compared to the sun. So if you have this, something equal to the sun, then it's going to be a 1. If it's higher than the sun, it's going to be brighter than the sun by that much. So you can have, like, here's 10,000 and then 100,000 suns. Okay, so that's how bright something is. Is it 100,000 suns? Well, that's a very bright thing. Is it much less? Is it a thousandth of a sun, or 10,000ths, or a millionth of a sun? So you can have very dim objects towards the bottom. You can have very bright objects towards the top. So when you put these four corners of the room together, you can say you can have cool objects that are dim. You can have cool objects that are very bright. So let's go here. So this is cool, and it's also dim. So if these are cool and dim, that means they must be very small, okay? Very small. If these are hot and bright on this side, okay, because they're towards the top and towards the left, then these must be very large, okay? Very large stars. And then you can also have large, so this would be large, but this would also be dim. No, sorry, not large and dim, large and cool. Sorry about that. Large and cool. But over here, you're going to have very hot, okay, but at the same time, not really dim. Strange. So you're going to have up here, let's do this first. If you have a large star that's also very cool, you're going to get red stars, okay, because that's going to be the cool side, but they're going to be very, very big. These are your giants, okay, so you have several giants. You even have some supergiants, and like Betelgeuse in Orion, okay, ridiculously big, huge stars, okay. Now they may not appear ridiculously huge in the sky because they may be very, very far away as well, okay. On the other side of this other side down here, you've got these dwarfs. So a dwarf would be, I don't know, like compare the sun and the earth. A white dwarf could be the size of the earth, much smaller than the sun, but yet much, much hotter than the sun. Okay, so we could see, well, what has happened? What made it hotter? What made it smaller and hotter? What made it cooler and bigger? And we'll look at that. Mostly you've got a fight. You've got a explosion on the inside wanting to go out and forcing it out as gases are being fused together and new elements are being made. And then you have gravity pushing in. And so there's always a fight between gravity and the pressures of these newly made explosions that's going on in the inside of the stars. So as we look at all stars, we can classify them. And this is probably the most useful way to do it, is an HR diagram. So I hope that helped you some, and I'll see you in class.